Alright, let's get started with week 10, our temperature sensor calibration. We're going to cover three primary things that are the activities this week. Our temperature sensor circuit is just a review of another simple 2-resistor series circuit, only this time it's being used to help provide input to our microcontroller. It's using a thermistor, a negative temperature characteristic device, as a temperature sensor, and so we'll review that in a second. We're also going to cover the programming. We do provide a program that reads the sensor input value, but in that program you'll have to take actions this week to calibrate the sensor and display the correct temperature. Finally, there's testing the heater and sensor operation. It's a 60-second heating activity that allows us to predict and verify the temperature change. It's a heat transfer activity, something that all young engineers have to go through. So we're going to get these three things done. Set this aside. Alright, so what does that temperature sensor circuit look like? Again, you won't be wiring this, but we do want you to see it's another application of Ohm's law here. So the UNO 32 has 3.3 volts and ground on it. This will be our power supply for this sensor circuit. Again, the 3.3 volts will come down through a 10 kilo ohm resistor and then down through the resistance of the thermistor, which is a negative temperature characteristic resistor. So this voltage across the thermistor is the voltage we're going to be watching with the UNO 32. So just to revisit, so it's another application of Ohm's law where the UNO voltage is equal to the two resistances added up times the current going through the loop. So the resistance will change with temperature, so in that case the total current will change, and when the current changes, the voltage through this changes, and that's what we'll be monitoring with this. Now this shows two pieces of the circuit. This shows, you notice we've got the arrows here showing that the UNO 32 is going to act like our voltmeter that we used in class to measure voltage, and so its probes will be connected across, or wires will be connected across the thermistor, and we'll be reading the voltage input on one of the analog inputs of the UNO 32. Again, it's proportional, the voltage will be proportional to the water temperature. Alright, so let's take a look. We're going to show you where the wiring is for this. Again, it's a 2-resistor series circuit. Let's take a look at this. So we've got 3.3 volts and ground, right? So we have to look closely here on the board and draw 3.3 volts coming out and ground. So let's look at the 3.3 volts first. Comes down to the terminal block and gets jumpered over into the rail of the breadboard. Now this breadboard, the two sides are divided, so we put jumpers in here for positive and negative, and so here the 3.3 volts comes across through the resistor, that 10K resistor that was on that circuit, and then out to the thermistor. So if we follow these wires all the way over, red and white wires will be going out to our thermistor. On the terminal block, they're tied in here, and then the thermistor is actually this device right here. It happens to be encased in a polymer, and so you go through this small resistor whose temperature varies as you warm it up. So we'll see the result of heating it with your hands or heating it with embedded in water. So it comes back and back to the board. And again, the other side of that resistor is here, and then it comes through to ground. And that ground comes back all the way up to the UNO 32 ground. So we have completed that circuit. Let's take one more look at that circuit just to remind you. Again, we went out of the 3.3, around through the 10K resistor. We went out to the thermistor, which happened to be a long set of wires, and then back onto the breadboard and back to ground at the UNO 32. So we completed this simple circuit, even though the wiring is longer and reaches across the table. So the UNO 32 programming, we're providing the program that will help you see how to read the analog input. We did do this with the light sensors from the the search program in our robot work in class. So again, the red lines here indicate that's where we're going to measure the voltage across this thermistor. And we'll do that wiring in just a second. But the key elements are we're going to use an analog read on one of the analog inputs to bring in a voltage value here. We'll create a function that will calibrate and calculate the new temperature that corresponds to the measured voltage. So this is the calibration activity we're going to be doing. Finally, we're going to serial print these values out to display the millivolt values off the thermistor, and then also the corrected temperature value all out on the serial monitor, so we can monitor the temperature in a corrected way. Okay, so let's show how the UNO 32 is being used as a meter here. Again, we're going to use an analog input, and if you remember on the UNO 32, we've got analog inputs on this pin set right here. So it goes 0, 1, 2, 3. And right now we're connected to pin A0. Pin A0 is going to act like part of the meter. It's going to come down to the board, jumper across to the point where the 10K resistor and the thermistor are tied together. Again, on that circuit, that's the point we wanted to talk about. So we're going to measure the difference between, potential difference between this point and ground. And so let's follow the other piece. And so we knew ground comes out and back here. So we're going to measure the voltage across, essentially across the thermistor. And in order to do that, we come back to the ground, comes back through here, and then back up to the board. So essentially we're measuring that voltage, and what the UNO 32 is seeing is the potential difference between the analog input 0 and ground. Again, let's take a quick look at that circuit again. So this is going to be our blue wire, and this is measuring connected to that point where the 10K and the thermistor are tied together. So that goes out to the UNO 32, and then the ground is also tied to that lower part of that circuit. We knew that was already set up on the series circuit that got the sensor powered. So this is the setup for that. Okay, now let's talk about the UNO 32 programming. Take a quick look at that. Alright, so we're going to take a look at that program here. Now this is the program that's downloaded from the online environment. Not much here. It sets up our serial communication for the serial monitor, goes into the loop function, and calculates, it gets a value from this using this function get temperature sensor. If you look down below, we have a separate function set up, and this is where it's using the analog read command. Happens to be using analog input A0. It's up to you how you use that. If we all keep it A0, it'll work better in class. Now once it gets that value, it returns it and calls it temp sensor volts, and so that's the value we're going to be graphing against the real temperature today. You can see there's also another formula here that uses that temp sensor volts value to calculate the Celsius value. This is the part you'll be correcting today with your calibration. So when it's all said and done, it displays both the volts value and a non-calibrated value for temperature in Celsius. Since you haven't completed the calibration, this isn't correct yet. So once you're done, you can modify this to move it to the calibrated value. We'll talk a little bit more about that later. But right now, it also displays this value every second. So this, set up the way it is, will allow us to monitor the temperature input. I'm going to hit the serial monitor here, have it pop up. Of course, it restarts the program, counts to about 4, and then starts reading. You'll notice here, temp sensor volts, it is reading, our circuit is done correctly. It's reading 512, and that happens to be millivolts. And then it's got a value for temperature, but it is not calibrated. So these are the temperatures we'll be watching and recording. Alright, so now it's time to get started on the temperature calibration. This really shouldn't take too long once you get a hang of what we're going to be doing. So this is the graph from the experimental data sheet. You should have this prepared ahead of time. We're going to have ice water, room temperature water, and hot water. We'll be taking the millivolt reading when the thermistor is in the data setting. That'll be placed here, and we'll also take an actual temperature reading using the thermometer. And so let's go ahead and take one set of data and then come back to this. Alright, so if we're going to take ice water, for example, we'll have it in the classroom. We'll have ice water, room temperature water, and then boiling water, and then we'll mix up the other samples. So for example, let's take the ice water. We actually don't have ice water today, but put it in here and then put our thermometer down in here as well. I better stick a little bit closer. There we go. So the thermistor and this sensor in there nicely. And as we watch that reading here, it's dropping down just a little bit, reading 26. Let's see how it stabilizes. On temp sensor volts, seems to have stabilized. I'll take another look. Yeah, it seems to have stabilized. So it happens to have stabilized at 540. And the thermometer seems to have stabilized roughly at about 25.3. It's dropping a little bit. You should wait for it to stabilize a little bit more. So we'll call this 25.2. Okay. As long as you take them at about the same time, the readings should be good enough to help you get this done. So that's the first sample. Pull this one out, set the ice water aside, pull in the room temperature. I think these are close to the same today. Get your second reading. All right, so let's take a look at this. I'm seeing 24.4 and 528. Oops, sorry, 528. Sorry, put that in the wrong spot. That's 24.4. So I have to fix that. All right, so let's do the hot water as well. This one we do have. You'll see a significant difference here. Pull the thermometers out. Move this back. Put in this, and here you'll see a significant difference. Temperature's climbing pretty rapidly there. And we wait for it to stabilize. Probably after about a 1-minute pause here, it's stabilized at 38.6 degrees on the hot side and 239 on the millivolts. So again, what you'll be doing is taking those three readings and then creating other samples. Let's go ahead and do that. I'm going to pull this aside here, and let's mix up the cold and the room temperature. That provides us another sample to get the temperature reading on. All right, and then the final sample would be room temperature and boiling. Allow us to get another sample. Again, add the thermometer, sensor to complete your temperature reading there. All right, so what's left to do for you? So we have to correct the program to calculate and display the correct temperature. Calculate, look at that, nice error there. Calculate and display the correct temperature. So that means you have to create two graphs. All right, one's going to be the UNO 32 voltage on the vertical and the temperature on the horizontal, and the other one's going to be the opposite of that. You should include both the y equals mx plus b trend lines on those two graphs, and then we're going to select which one of those lines best allows you to calculate the actual temperature from the measured value of millivolts. And then we'll test the resulting output on the monitor. So again, you're going to select the line that has the correct values that allow you to convert this on the program. We're going to insert those values into the program and then test it out. Repeat the measurements you've just taken to see if the values read where they need to read. Once you've done that, you can modify the program to say that it is calibrated. The final activity you'll do in class is to check the heater and sensor testing. All right, we want to predict, create a temperature change, and then measure that temperature change. All right, so we'll get to the formula here a little bit, but one thing you're going to need is the volume of the tank or the mass of the water. Right? Also, from week 9, you're going to need the power data from your heater. How much power is your heater delivering to the water when it's submerged? And then finally, we're going to predict that temperature change. This is the graph that's shown on the data sheet in the online materials, and you'll be completing it. It gives a place for the tank volume that you'll measure, the calculation for the number of watts that your heater is putting out, the expected temperature change, and so then over time we're going to heat for 60 seconds and then wait another 60 seconds and watch the temperature. Okay, moving on to the next piece here. So let's do a little bit of that temperature change. Again, the formula we're using has the heat transfer is going to be equal to the mass times the specific heat and the change in temperature. So if we want to know the change in temperature, we solve for delta T here. The heat added to the system is going to be found from your power calculations. So that's going to be power times time is going to be our total number of joules added to the water. We're going to use the specific heat here for CP, and then the mass of the water that you'll need to figure out the mass for the tank. So we're going to run the program displaying temperature for one sample per second, run the heater for 60 seconds again, and this is again, run it for 60 seconds, then shut it off and continue recording until it stabilizes. Going to 120 seconds should be fine. So you're going to have a graph that's going to show this. I'll show you a better one in just a second. So that's the final data of your collection, completing that data sheet and then creating this particular graph. Alright, so here we're back looking at the screen, and then clearly it's running through taking a temperature sample each time. I'm not showing the calibrated piece. By this point yours will be calibrated. The readings will be. So let's close this as we're getting ready to start the heater cycle, and then restart it. As soon as you're ready to start heating, you're going to select serial monitor again. It will restart the program and start collecting data. Alright, so rather than have you use the programming to turn on the heater today, we're going to jump add power using a jumper wire. And so this is what it says in the data sheet. So I trimmed off, I have a nice long red wire to make it clear that we're using the 3.3 volts. And again, I've tied it in here. And remember, the relays are activated when the UNO 32 provides 3.3 volts out of a digital input. So if we want to activate the heater, we can go to the same location and touch this. You should see this green light come on. So that means the heater is on. So we'll use this to do our 60-second heating activity. You can reset your programming and the serial monitor to start new readings, and then you can plug it in and start the heater. Alright, so you'll be running for 60 seconds. When the 60 seconds is over, unplug this and continue recording your temperature. Alright, so just a quick reminder on how to check the volume of your tank. So the tanks have the pump in them and the heater, and so we want to fill it up until it overflows, because that'll be the normal part. So I'm going to go ahead and measure the total volume of this glass of water, and we got about 440 grams. I know that's more than our tank can hold, and I'll do my best to minimize our spilling, and we run it up until it overflows. So you can see down here it's overflowed, and we'll return the overflow water back into the cup, and now we have, out of our original 440, we have 158 left. So from that you can figure out the mass of the water in your tank. Alright, so one last reminder. So you need these graphs done before the end of class, and so again you're going to have 3 graphs total. Two from your temperature experiment with the UNO 32 voltage versus temperature, and then UNO 32 temperature versus the UNO 32 voltage. Here you're going to have y equals mx plus b trend lines added that are not shown here, and you're going to select the correct line to complete your calibration. Finally, you're going to have a graph for the 60-second heating test that's going to show some temperature rise over a 2-minute period. Again, the heating only goes for the first 60 seconds, and then you observe the temperature beyond that.